So the next topic is coherency. Okay, coherency. And I know this you have already read in your power system stability, but here we will be doing on an equation coherency. So we'll be seeing the coherency in more clear way on the basis of our swing equation. So we have derived our swing equation as 2h upon omega s d square del upon dt square pa. Pa is the accelerating power, and that is our ps minus pe. Okay, now here uh, these two machines G1 and G2 is your G1 and G2 is your two generator, and next is your this connected to same bus. Okay, one bus system. This is your bus bar. So these two machines are connected to one bus. Now if the demand of electrical power increases, then we need to increase the mechanical power. Now this increase in the mechanical power may affect both the machine in similar way, or may affect both the machine in a different way. That means what? If there is same change in the angle, that means delta 1 and delta 2 is same for if there is increment in the power, that means if these two machines are swinging together, that means they are coherent. If delta 1 and delta 2 are different, that means these two machines are not swinging together, that is non-coherent. Okay, now we'll check it here. Suppose I am writing the swing equation for first machine, that is G1. Now I am putting it delta 1 and here P1 and E1. Okay, so this is my swing equation and this is my H1. H1. Now the same equation for our P2 or generator 2. So what I can write, 2H2 d square d delta 2 upon dt square so PA1 it is, so I'm putting it PA2. So PA2, that is equal to PS1 minus PS2 minus PE2. So these are the two equations for two different generators. Now I am assuming is that these two machines are swinging together. That means I am assuming that delta 1 is equal to delta 2 is equal to del. Okay, so this is my coherent. These two machines are coherent, that is these are swinging together. So what I can expect with this, so if adding these two equation, adding 1 and 2, adding 1 and 2, you can get, adding 1 and 2, so you will get I'm just making it simple, 2 omega s h1 plus h2. Okay, h1 plus h2, and then d square del upon dt square, because these two are the same terms, and then ps1 plus ps2 minus pe1 minus pe2. So I'm taking the minus common. So what I can write, this is the equation. So this is my equivalent mechanical output and this is my equivalent electrical output. Okay, this is my equivalent mechanical input and this is my equivalent mechanical output, and this h1 plus h2 is my equivalent. H1 plus H2 is the equivalent um, for our this inertia, right? Okay, So this is the final terms which I can write for the equation. Okay. Now the will defined for the next part, that is our non-coherency part. Okay. Now for the next part, that is your non-coherent part, I will discuss it like the same equation. If you put for these two, that is 2h1 upon omega s d square del 1 upon dt square ps1 minus pe2 pe1, sorry, and 2h2 upon omega s d square delta 2 upon dt square ps2 minus ps2 minus pe2. Now here del 1 is not equal to del 2, that means the swing is not constant. That means the electrical and the mechanical change is affecting both the generator are in a different manner. So what I can write is that there is I can say if del 1 gets increased, del 2 will decrease. That means there is a negative change in your angle. Okay, so there is a negative change in the angle. That is what I can write. So talking about this, so I can change something previously, because in the previous term both the del 1 and del 2 was equal. So we haven't done anything new. Now I'll do something because of that only. I am changing my previous equation, just changing like this. So I'm changing this part, uh, this part. I'm changing it to that side. I'm bringing it to that side. Okay. So what I can write here, I can write it like this. So I will write it delta d square delta is equal to omega s upon omega s upon 2 ps1 minus pe1 upon h1. Okay, so now I haven't done anything new, just brought that term that side. Similarly with this equation also I am going to do this thing. I am doing this because right now the concern is with a delta. Okay, so that's why there is some changes I am doing with the equation, because it is easy when there is a equal changes, but it is difficult when there is when the change is different. Okay, omega s upon 2, so you can write ps2 minus pe2 upon h2. So these are the two equations. Now if I see that there is a different change, so I can write that there is a subtraction in the subtraction, or different change means there is dissimilarities. So I can say that these two, on subtracting these two terms, I can write d square delta dt square del 1 minus del 2. So this is the change actually. Okay, change is what? Omega s upon 2, omega s upon 2, and next is ps1 minus pe1 upon h1 minus ps2 minus pe2 upon h2. Now in the previous equation, if you check around, I haven't added the delta 1 plus delta 2. I haven't added, I have written it directly delta. Okay, because there is a similar change. change I have to work on. I have to change. I have see the change in the delta. So the change is quite similar. That's why I haven't read it. It should not be 2 delta. Okay, the double of the change. It's not correct. Now, this is what the change here. Change is similar. Now here the change is quite different. Delta 1 might be changing with quite different way in delta 2 kind might be changed. That's why I'm more concerned on delta. Differentiation always means when there is a change in something. For if there is no change, that means there is a constant thing, then the differentiation will be zero. Okay, so you must have notice it, and you might be having that query. So please be sure that while differentiating, you have to concerned about the change. Okay, now once I got this equation, I'm going to multiply this equation with one term, that is h1 into h2 upon h1 plus h2. I'm multiplying it both side. Okay, so here I have multiplied with this term. Similarly, I have multiplied with this term h1 plus h2, sorry, h1 into h2. So I am multiplying this term like this: omega s by 2 h1 into h2 upon h1 plus h2. Okay, so I'm multiplying it. Now what happens with the multiplication part is that if you get it inside, you will see the change. So I can write again 2 upon omega s h1 h2 upon h1 plus h2 d square upon dt square. So this is my equivalent, del 1 minus del 2. So I will write it, multiply it inside, and just separate the s1 s term and e term. So you will get the term like this: ps1 h2 ps1 h2 minus ps2 h1 upon h1 plus h2. Okay, and next pe2 pe2h2 minus, sorry, pe1 p1h2 pe1h2 and pe2h1 upon h1 plus h2. Okay, so this is the two terms which you will get once you multiply and once you equate all the both the equation. Okay, so there may be sign change. It goes inside. So h1 we can change like this, minus sign inside. So pe2h2 and you will get like this. Okay, so you can do like this. So this is the equivalent. Okay, this, and here it will be plus. Okay, sorry. So this is what our equation will seems to. You do it yourself. I have done by myself, and just see what is the effect. So what I can say here, you have read the equation till here, H equivalent, and you have derived it directly. But here what I have done here, I have changed it. I have done it with the equation way. Okay, so what I can say is that H equivalent will be H equivalent will be h1 plus into h2 upon H1 plus H2 for a machine that is non-coherent. And what is our effective equivalent mechanical side is PS1 H1 H2 plus PS2 H1 upon H1 plus H2. Okay, and mechanical side PS, and what is our electrical side? Electrical side will be PE1 H2 plus PE2 H1 upon H1 plus H2. So these are the two different equivalent equations that is new to your knowledge for electrical side, okay, and mechanical side power increment. Next we'll do some numerical, and better you have to do that numerical based on that. Now here only you have learned about the base quantities, what how much base you have to find out, and you have derived it in the previous, like H1 upon H equivalent is equal to 1 upon H1 plus H2 plus H3, like this, okay, H2, and like this. If the number of machines increases, when the machine is in swinging together, so you have written 1 upon H1 plus H2 plus H3, like this. The next part is the power angle equation. Power angle equation of a two machine here of a two machine system. Actually we have to define for a multi machine system, but we are taking a reference of a two machine system. So this is a network where you can find that you have bus 1 and you have two bus, and there is a two generators E1 and E2 that are supplying the current to the system, and this is the reference node. Okay, so when you might have learned in the load flow analysis that for a two machine system, Y bus is, you can say Y11, Y12, Y21 and Y22. So this is the Y bus system for this two machine system. So this is bus 1, bus 2, 1 and 2, right? So this is how it goes on. So why I am again remodeling or redefining this equation, because you might have learnt about that the power angle equation is EV upon XS sine delta, right? So this here in this term, the major part is of XS. Because of XS, there is no real part. Real part means the in the resistance part you are not having, here you don't have resistance. This resistance is negligible, okay, but for a transmission system there is also a resistance as well as an inductance. So I am making uh, uh, this analysis based on our load flow analysis, and then we can redefine our uh, power equation. Okay, then we will see what part we are actually missing. We will get to know that which part actually we are missing in the from the previous analysis. Okay, so now this is our Y bus for a two bus system. Then suppose these are the currents I1 and I2. Now I am just specifying that there is a current at a bus IK. Some IK bus is current is flowing. So what I can write about IK in terms of Y. So Y is, I can say that this is an admittance. So I can write the admittance of that bus with respect to concerned bus and the voltage of that bus, so V1. Okay, so this is the IK for bus 1. Now if k is attached to, suppose this bus, there is a bus and this is kth bus, and this is attached to 1, this is attached to 2, this is attached to 3, and so on up to n. Okay, so up to n. Now this bus has number of buses, so the current that is going to flow from, if I write the current of this ik bus, what I can write, so ik1 v1, so I can write ik2 v2 plus ik3 sorry, yk3 yk3 v3, and so on up to ykn vn. Okay, so vn, so this is my ik equation, and in the summation way form, if you can write it, ik is summation n changes from. Now here if you see here the quantity y, and now this is my n quantity, small n, so sorry, this has to be capital N. This is the last quantity we have, yn. Okay, so this has to be capital N. So this I am writing it like this, so yn, okay, capital N. So here small n changes from 1 to capital N. Okay, so I'll write it yk small n v, and this will be n v small n. Okay, so this is how you can write the equation. Now ik of this equation is yk1 v1, yk2 v2, yk3 v3, and so on up to ykn vn. Okay, next is, if I want to define the apparent power at kth bus, what I can write, so apparent power is nothing but pk plus jqk, right? And this is what vk and ik star, this is what we are using in the power equation. So what I can write about vk, so vk into summation ik, in place of ik and putting it like this, 1 to n ykn vn, and the most important part is the conjugate. Okay, so this is how I have written the power equation and their number of bus. Now looking at this system here, if you check, there is a 2-bus system. So what happens to our capital N? So capital N will be 2. So this is the maximum 2-bus system which we have. Now what I can write about our SK? So SK I can write like VK summation n, it changes from 1 to, now the capital N is 2, so I will write it 2 ykn vn and conjugate. Okay, so I can write it, I can expand this like vk vk. Okay, now ykn n, so 1 v1 star, okay, plus vk into yk2 v2 star. So this is how your equation changes. Now if I am talking now this kth bus, if I am taking this kth bus as bus one number 1, so kth bus is my bus number 1. So what I am doing, actually I am calculating the power of the bus number 1. So I will replace this power. So I will replace this k with 1. Okay. So I'll just replace this k with 1. So we need not to go. Okay. So I can first I'll put here k. So this is my original equation. So my S power at reactive power, apparent power at bus number 1 is y1. I am replacing k with 1. So this is how our equation got changed. Now in the next we have done the equation which we left with was S1. S1 was V1 Y1 1 V1 star, okay, and then V1 Y12 V2 star, right? Now here if you check the bus number 1 and bus number 2, here you will find voltage. So V1 is equal to E1, V2 is equal to E2, okay, taking this ground, right? So this is our V1. So I will replace V1 with E1 Y1 E1 star plus V1 Y12 E2 star. Okay. Now I'll make some assumption. Assumption is like E1 has magnitude E1, okay, and at an angle delta 1, okay, and E2 has an angle this and has a magnitude this and at an angle delta 2, and y1 1 is equal to g11 plus jv1, okay, and y12 is equal to g12 plus jb12, and here I am just replacing one thing, that is y12 at this as y12 at an angle theta 12, okay. Now I am not writing this in angular form because this is the self admittance of the branch, okay, self admittance of the branch. So this will not vary the current, okay. Now I will tell you why, because this makes my power equation much easier, okay, comparatively. If I don't use it, we'll check it right now. We'll check it right now. Now if I put the values, what I can write about, now this is, I am hearing it, putting it like P1 plus JQ1, right? So I can write this in the form of, so S1 I can write E1. So E1 is magnitude E1 and at an angle magnitude E1 at an angle delta 1. Y1 you can write G11 plus JB11, okay, multiplied by E1 magnitude E1 at an angle delta 1 and star, okay, plus, okay, here it should be E1, okay, I missed it. This is E1. Now here I will write magnitude E1 at an angle delta 1 and multiplied by, I'll put this form, angular form, because of something I'll tell you. Y12 at an angle delta theta 2 multiplied by E2. E2 is magnitude E2 at an angle delta 2. Okay, and why I'm putting it like check here. Now if I want to take the real part and the reactive part, now this conjugate, if I remove this conjugate, what happens to the conjugate part? Conjugate what part will negative my equation. Now here this sign changes to minus. Okay, if I remove this conjugate. Okay, and this delta also changes to negative delta. Okay, now this changes to negative delta. Similarly here also it happens. So conjugate changes and delta 2, and here also delta theta 1 2, and the sign changes. Now what happens if you multiply this inside, if you multiply E1 inside, so this delta 1 plus minus delta 1, so that gets cancelled, right? So that gets cancelled, so it will be easier to form. Here it does not happens, delta 1 minus delta 2. Okay, so that does not comes here, so it is easier to form here. So what I can write here is that taking about real power, I'm just concentrating on our real power, so I'll write only real term. Okay, so this is my real term, this is my real term, this is my real term, and cos of these terms. Okay, so I'll write it like this: E1 mod E1 square, okay, G11. Okay, and then this is the term coming from this only, that's it, nothing else. E1 G11 and delta 1 minus delta 1, that is 0, so that's not coming here. Now from here if you check the real term, so you'll get E1 mod E1 mod E2, okay, mod Y12 at an angle, sorry, not angle, cos of delta 1 minus delta 2 minus theta 1 2. So this is the same one term you will get from this. Similarly, if you find out Q12 Q1, so here if you find out Q1, so just go for the imaginary term. So here if you JB1, right, so that is minus sign is comes here, so I will write E mod E1 square B11, okay, plus this comes from this bracket, and the next comes from E1 E2 Y12 sine del 1 minus del 2 minus theta 1 2. So this is the equation which we got from the assumption by assuming. Now there is some modification here, in the further class we'll see the modification part.